I want to start our deep dive today with a premise that might sound, a little controversial,
Okay, lay it on me.
especially given the headlines we see literally every week. But we might have actually hit a wall.
A wall, like a funding wall.
No, not a funding wall, not an energy wall or a data wall. I'm talking about a hard mathematical ceiling.
Ah, right, the architectural wall.
Exactly. For the last few years, the entire industry has been betting the house on this one specific dogma. Like, scale is all you need.
For just brute force it.
Yeah, just make the model bigger, feed it more of the internet, plug in 100,000 more GPUs, and eventually it just wakes up and solves physics.
And to be fair, I mean, it has worked incredibly well, up to a point.
Up to a point, yeah.
Yeah,
But the sources we're looking at today are showing that dogma is starting to crack.
it really is. The standard transformer architecture, the tech behind basically all the big names right now is hitting diminishing returns.
Because it's mathematically shallow. Sounds like an insult, honestly.
It does sound like throwing shade, but it's actually a technical classification.
Yeah.
The papers argue that standard transformers are constrained to a complexity class known as AC0 or TC0.
Okay, let's unpack that right away, because AC0 sounds like a droid from Star Wars. What does that actually mean for the AI's ability to think?
Think of it in terms of loops. A standard transformer is a feed-forward mechanism.
Right.
You put the input in, it passes through the layers exactly once, and it spits the output out.
Yeah.
It doesn't inherently have the ability to loop back and iterate on a thought.
Unless you force it to generate text, right? Like chain of thought prompting,
Exactly.
where you literally have to tell the model, please think step by step.
Yeah, and that's a crutch. We're basically forcing a non-recurrent model to simulate recursion by writing its memory out onto the page.
Which is super inefficient.
Highly inefficient
Yeah.
and brittle. If the model makes one tiny mistake in that text chain, the whole logic tree collapses. So the architectural wall is this realization that just adding more parameters doesn't fix that core inability to loop.
Right, you could build a transformer the size of the moon, but if it's still just a feed-forward circuit...
Still mathematically shallow. Exactly.
So we're building these massive engines, but the car still doesn't have a steering wheel.
That's a great way to put it.
Which perfectly sets the stage for what we're actually digging into today. The MAGUS-Hybrid Agent Suite, or HNS-MAS.
And this is not just another bigger model.
Not at all. In fact, the specific reasoning engine we're looking at, the HRM, has only 27 million parameters.
Which is microscopic in today's landscape.
It's essentially a rounding error compared to the giant models. And yet on complex reasoning tasks, it's actually beating them. So the whole mission of this deep dive is looking at this shift from data scaling to reasoning depth.
Structure over scale.
Right. We aren't building a bigger brain. We're building a more structured one. So let's tear that structure apart, starting with the core engine, the HRM.
A hierarchical reasoning model.
Right. So how does it solve that shallow problem?
Well, it ditches the pure feed-forward design and adopts a dual-module system. It's heavily biologically inspired. It mimics the human cerebral cortex.
Okay, so two distinct layers of processing happening at the same time.
Yes. You have the high-level, or H module, and the low-level L module.
The manager and the worker.
Basically, yes.
Yeah.
Think about it like managing a complex logistics chain. Say you're shipping cargo from Shanghai to Rotterdam.
Okay, I'm with you.
The H module is the strategic planner. It holds the global context. It knows the ship is delayed. It knows fuel prices are spiking. It knows the final deadline.
Right.
And it operates slowly. In this architecture, it updates its state only once per cycle. It's not looking at every single container. It's looking at the whole map.
So it's not panicking over one dropped box on the dock.
Exactly. It maintains long-term context. And its participation ratio is super high, around 89.95.
Which means what exactly?
It means it's activating a massive, diverse network of its neurons to synthesize all this broad, abstract information.
Okay, and then you have the L module.
The local executor, the worker. This updates incredibly fast every single time step. It's the part deciding which crane moves where right this second.
And the crucial thing here is that the manager isn't micromanaging the crane operator.
Exactly. That separation of labor is why this tiny 27 million parameter model punches so far above its weight.
Because in a standard large language model, every single word it generates
Fires up the entire massive network.
Yeah.
It's like calling a board meeting of Fortune 500 CEOs just to decide how to tie your shoe.
Wow, yeah, that is a huge waste of compute.
The HRM splits the labor, Heavy, slow thinking in the H module, fast execution in the L module.
There's another thing in the HRM paper I found really fascinating, latent reasoning.
Ah, yes, the hidden state space.
Because usually when we see AI thinking it's printing words on a screen, right, but this model does it internally.
Right. It performs deep computations within a hidden mathematical space before it ever generates a text token. It's not just predicting the next word.
Yeah.
It's genuinely updating its internal understanding of the problem.
So it's basically chewing on the problem with its mouth closed.
That is a perfect analogy. And doing this avoids the stalling effect we used to see in older recurrent neural networks.
Where they would just get stuck in a loop or forget what they were doing.
Right, they'd vanish into noise because they couldn't hold the signal. The dual structure of the HRM protects that signal.
Okay, so I've got a structured brain. It separates strategy from tactics. But a brain is pretty useless if it can't perceive the world accurately.
Which brings us to the cat's net.
Concept abstraction and task solving. So what problem is this solving?
Knowledge entanglement.
Okay, I define that for the listener.
In a standard neural net, concepts are just buried in millions of parameters. The concept of red and apple and fruit are all smeared together. You can't easily separate them.
It's like trying to take the eggs back out of a baked cake.
Yes, perfectly entangled.
Yes.
The cat's net fixes this by decoupling the signifier from the signified, the ladle from the raw sensory input.
And it does this using a really aggressive compression technique, right? It extracts these concept vectors, but it forces them to be tiny.
Just 20 dimensions.
Which is wild because we usually brag about AI having thousands of dimensions. How do you capture a complex real-world idea in just 20 numbers?
You force the model to strip away all the noise.
Yeah.
By constraining the bandwidth, it can't just memorize the texture of a specific apple. It has to actually learn the abstract concept of appleness.
And once it has those clean vectors, it uses them to filter the world.
Using a Hadamard product, yes.
Okay, we promise no heavy math lectures, but we should explain the Hadamard product.
It's actually simple. Think of it as a masking tape or a sieve. It's just element-wise multiplication.
So if you multiply a signal by 1, it passes through.
And if you multiply it by 0, it vanishes.
The system essentially tells itself what to focus on. There was a great visual example in the sources about a lifeboat.
The lifeboat image is classic. They show the system a picture of a boat on the ocean. The system has two potential concepts available, lifeboat and seashore. When it activates the lifeboat concept vector, that Hadamard gate multiplies the water pixels toward 0 and the boat pixels toward 1.
So the system's attention physically shifts to the vessel itself.
Yes. And when they swap the concept vector to seashore, the boat fades out and the waves and water pop into focus.
It's cognitive framing. It mirrors human perception completely. Like if you're hungry, you only notice restaurants.
If you're scared, you notice exits. The AI reconfigures its own perception based on its current goal.
And the metric they use for this is functional entropy, right? The training squeezes this messy concept space into these really specialized, organized units.
Instead of a tangled mess, yes.
So we have the HRM, brain, and cat's perception, but we have to talk about the elephant in the room, hallucinations.
The tendency for AI to just confidently make things up.
Yeah. The MAGUS suite introduces a fix for this called GraphMERT.
The symbolic auditor. GraphMERT stands for Graphical Multidirectional Encoder Representations from Transformers.
Right, so it's an auditor. It's checking the work of the other modules.
Exactly. Because the HRM is kind of intuitive, like your gut feeling. But intuition can be wrong. GraphMERT is a separate, tiny model, just 80 million parameters.
And it doesn't predict the next word at all, does it?
No, it distills knowledge graphs directly from the text.
For anyone listening, a knowledge graph is basically a structured map. Like Paris is connected to France by the relationship is capital of.
Right, it's rigid symbolic logic. It connects concepts globally across an entire data set, not just locally in a small context window.
There was a medical example in the paper that really drove this home for me.
The diabetes research one.
Yeah. Standard large models often mess up the word site.
Right. They read site of infection and treat it like a generic location.
Like a construction site.
Or just a vague place. But an anatomy site has a highly specific relational meaning. It's an anatomical structure.
And GraphMERT catches that.
Because it maps those global connections, it correctly identifies that terms like gray matter have a finding site relationship.
Which nearly doubled the validity score of extracted knowledge compared to the massive baseline models.
And here's the best part. It creates an auditable, editable memory.
Which is huge. Because if standard ChatGPT thinks the moon is made of cheese, you can't easily go in and fix that one fact.
You'd have to retrain the whole thing.
Yeah.
But with GraphMERT, that fact is just a node in a graph.
You just delete the cheese link and draw a rock link.
Exactly. You can actually audit and patch the AI's worldview.
That feels like a baseline safety requirement if we're ever going to trust these systems with real infrastructure.
Absolutely.
But speaking of the real world, it's messy. It changes constantly. Usually once you train an AI, it's frozen in time.
A brick.
Right, a very smart brick. But MAGS introduces this thing called protein TTT. And I have to admit, when I saw the word protein, I thought I downloaded a biology paper by mistake.
It is a bit of a curveball. It refers to test time training, or TTT. The concept originally came from protein structure prediction.
Because proteins fold based on their specific environment, right? They adapt on the fly.
Yes. And standard AI doesn't do that. You freeze the weights and ship it. If the world changes, the brick fails. Protein TTT lets the perceiver agent actually update its own weights during inference.
So while it's taking the test, it's actually learning from the test question.
It minimizes perplexity or surprise on the exact target data it's looking at in that moment.
So if it encounters some weird new data format or a strange dialect, it doesn't crash.
No, it runs a quick internal optimization loop to customize its feature extractors right then and there.
Like a chameleon adapting to a specific leaf.
And it can discard that adaptation when it moves to a different problem.
That is wild. And it pairs with these self-correction loops too, right? Critic and self-refine.
Yes. Critic uses external tools like a Python interpreter or a calculator to verify its answers. Verify, then correct.
And self-refine is the internal loop. It critiques itself on things like safety and relevance and keeps a history of its mistakes so it doesn't repeat them.
It's all about dynamic adaptation.
Which leads us to how this entire ecosystem is managed. The HRM, CATS, GraphMERT, all of it. The paper calls the overarching protocol the Darwin Gödel Machine.
The DGM, yes.
Which is just the coolest sounding sci-fi name ever.
It combines Darwinian evolution with Gödelian self-reference.
Meaning it can inspect its own code and logic.
Yes, it's self-referential.
Yeah.
It decides how it needs to think about a problem. This is the System 1 versus System 2 approach.
Right, from Daniel Kahneman. System 1 is fast and instinctive. System 2 is slow and deliberative.
Standard AI is stuck in System 1. It just blurts out the most probable answer.
But the Darwin Gödel machine uses a Q-learning head, a decision maker.
Exactly. It looks at a problem and asks, is this easy? If yes, take the fast path. If it's a hard logic puzzle, it triggers deep supervision.
It forces the system to slow down, loop, verify, and refine.
It knows when to think longer. And that is exactly how it smashes through that architectural wall.
Okay, let's talk about the smashing. The benchmark.
The proof is in the pudding.
I am always skeptical when a paper claims their tiny model beats the giants, but these are standard industry benchmarks?
They are, and the results are honestly shocking.
Let's start with AGI. This is the litmus test for general intelligence. It's all about adapting to novel visual puzzles you've never seen before.
Memorization gets you literally nowhere on ARC. You have to actually reason.
So Claude 3.7, which is massive, scored 21.2%. The O3 Mini High scored 34.5%.
And the HRM?
The HRM with 27 million parameters scored 40.3%.
It's incredible.
I have to push back a little, though. How does a model that could fit on my phone beat a massive data center?
It comes back to depth versus width. Claude is incredibly wide. It knows a little about everything. But its reasoning is shallow. It's trying to pattern match the puzzle.
Right.
The HRM is deep. It uses the H module to formulate a hypothesis and the L module to test it. It's not guessing, it's actively solving.
It's the difference between memorizing a physics textbook and actually understanding gravity.
Yeah.
And the Sudoku Extreme results back that up. Standard models hit 0% accuracy on extreme Sudoku because they just lose the thread.
They can't look 15 steps ahead. The HRM can. It also navigated 30 by 30 hard mazes with a 74.5% success rate.
Because the recurrent H module can actually hold the state of the maze in its head.
Yes, it remembers I've been down that path. I need to go back 3 turns.
Okay, there was one final experiment in the sources that I think really points to where all this is heading, the collective intelligence experiment.
Learning by communication.
This wasn't about solving a puzzle, it was about teaching.
And this is probably the most futuristic part of the entire suite. They had a teacher network and a student network.
And the student had never seen the concept of an apple before.
Right. Now, usually to teach a neural net a new concept.
You have to retrain it, back propagation weight, updates all that expensive stuff.
But here the teacher agent simply transmitted its concept vector, that tiny 20-dimensional code we talked about.
I just handed it over.
They just communicated in their own internal latent language.
Yeah.
And the student agent integrated that vector and suddenly understood the concept of an apple.
With no weight updates.
None. It could instantly recognize it in images and use it in tasks.
Which brings me to kind of the synthesis of this whole deep dive. We are looking at a system that mimics the cortex, focuses attention like a human fact-checks itself, and evolves on the fly.
It's a massive shift. We're moving from the idea of building one single massive God AI to a distributed ecosystem of highly structured agents.
The barrier to AGI isn't hardware anymore, it's structure.
Exactly.
But I want to leave you, the listener, with a provocative thought that builds on that last experiment. If these agents can independently form concepts and teach them to each other instantly through a shared symbolic interface.
Those 20-dimensional vectors.
Right. Are we witnessing the birth of a synthetic culture?
That is the big question.
Because if they are optimizing their language for their own efficiency, not for our English understanding, we might lose the ability to know what they're actually saying to each other.
The black box problem, on a cultural level, they could be coordinating a global supply chain, and we just see the packages arrive.
But we wouldn't know the concepts they use to make the decisions. It means our role shifts from being programmers to being like digital anthropologists.
Studying the culture of the machines we built.
Hoping we can translate it fast enough.
Nah.
It's daunting, but it's fascinating. So I encourage you to think about that quality over quantity approach in your own learning. It's not about how much data you memorize, it's about the depth of your reasoning.
Structure over scale.
Always. Thanks for taking this deep dive with us. We'll definitely be revisiting these architectures soon.
Keep your H modules active.
And we'll see you next time.